Hi everyone, thank you for joining. We will continue our discussion of linear regression series by discussing inference for a simple linear regression model. Before introducing the concept of slope inferencing, for example, I will cover our simulation framework that constructs the linear regression model that we will refer to in the subsequent slides. Here I am simulating a linear regression model with a slope of 4.2 and with noise that is randomly distributed with mean of 0 and a standard deviation of 2. If you remember from the previous video, this model satisfied all assumptions of linearity, constant variance, and normality. Here I'm looking at the summary function of this model, and we can see that the slope on the x coefficient is approximately 4.24. We can interpret the slope such that an increase in the x variable by 1 unit results in an increase in the y variable or the outcome by about 4.24 units. We can also see that this coefficient is statistically significant at an alpha level of 0.05. Next, we would like to gauge the variability in the sample slope estimate, i.e., is there considerable evidence that the population slope differs from 0 based on the sample slope returned from the linear regression model output. For this purpose, we would need to perform inference on the slope from the simple linear regression model, where we only have one explanatory variable. To compute the t-test statistic, we can divide the slope estimate by the standard error in the slope estimate, which quantifies the amount of variation in the slope estimate from one random sample to another. After determining the test statistic, we can compute a p-value by referring to a t-distribution with an n-2 degrees of freedom, where n is the sample size. I don't show that computation here, but it can easily be computed using statistical software. So right here we are computing the t-statistic using the simulated data. So we divide the slope estimate, which is 4.2376, by the standard error, which is 0.0241. And we get the t-statistic value to be 175.8. While I'm not computing the p-value here, we can reject the null hypothesis that the true slope is 0, given that the test statistic is far from 0. But for certainty, we would compute a p-value. Next, we can compute a confidence interval for the slope estimate to quantify the accuracy of our estimate. In the expression given, we would multiply the critical value for the t-distribution with n-2 degrees of freedom by the standard error of our coefficient and subtract that product from the model slope coefficient. The critical value for a 95% confidence interval is 2.05. So in the next slide, I will show an example of an exact confidence interval computation. So in this slide, we are computing a confidence interval for the slope estimate on x. We use the estimate and the standard error with a 2.05 critical value to compute the confidence interval. Here, the confidence interval is 4.1882 to 4.2870. We can interpret the confidence interval as that we are 95% confident that the population slope is between 4.188 and 4.287. Here, this is an important slide since we are exploring the concept of variation partition using the analysis of variance, which is also known as ANOVA. We are partitioning the total variability in our outcome into two components, which include the variation accounted for by the model, i.e. the model sum of squares, and the variation unexplained in the residuals, random errors, i.e. the error sum of squares. The equation above represents the summation symbol over the difference between each observation and the mean sample value, which represents the sum of squares total between the fitted value predicted by the model and the mean sample value, which represents the sum of squares model, and each individual observed value and the predicted fitted value, which represents the sum of squares of the error. We then sum the square of each term and add the sum of squares model and the sum of squares error squares to get the sum of squares total. In this slide, we are applying the concepts from the previous slide to practical implementation with the same original model. We are computing the analysis of variance on this model. Following this computation, we get the sum of squares for the model and sum of squares for the residuals/errors. We sum up both values to get the total sum of squares, which in this case are 125,376 or 125,376. In addition to the total sum of squares computation, we can also compute the ratio of the model sum of squares to the total sum of squares to thereby compute the coefficient of determination, or r squared. R squared quantifies the proportion of variation in the outcome y that is explained by the explanatory variable x in our model for a simple linear regression model. We also know that the square root of this coefficient of variation is the correlation coefficient. In this current slide, we again have a practical implementation of the coefficient of determination computation, where we are using the ANOVA model output to compute the ratio of the model sum of squares with the total sum of squares. In this case, the model sum of squares is 121,454, while the total sum of squares are 121,454 plus 3922. The ratio equals 0.969. We can interpret this quantity as such that approximately 97% of the variation in the outcome variable y is captured by the explanatory variable x. We can additionally use the coefficient of determination to rank and compare different models. In this equation, we are relating the sample correlation coefficient with the standard deviation of the outcome and the explanatory variable to relate the sample slope with the sample correlation between the explanatory and the outcome variables. This equation moreover shows an equivalence between hypothesis testing for the slope and for the correlation coefficient, which is also especially useful in the case that we do not need to directly construct a linear regression model to perform inference for the correlation coefficient. We can also convert this equation such that we can compute the sample correlation coefficient using the sample slope and the standard deviations for the outcome and the explanatory variables. In this slide, we are first constructing our sample linear regression model and then computing the standard deviations of the outcome and the explanatory variables. Then, we are using the sample slope along with the standard deviation estimates to compute the sample correlation coefficient. We are dividing the standard deviation of the explanatory variable by the standard deviation of the outcome and then multiplying the quotient by the sample slope. In this case, the value of the correlation coefficient is 0.9842. Lastly, we are performing inference for the correlation coefficient using just the sample correlation and the sample size. Here we are assessing whether the population correlation is equal to 0 null and whether the population correlation is not equal to 0, which is the alternative. This is convenient since we only need the sample correlation and the sample size to compute this test statistic. Given that the conditions of a simple linear regression model, including linearity, constant variance, and normality hold true, we can compute the p-value using the t-distribution with n-2 degrees of freedom. In the computation here, I'm calculating this test statistic by first calculating the correlation coefficient, which is based on the previous slides is 0.9842. I'm then using the formula from the last slide and a sample size of 1,000 to compute the test statistic, which comes out to be 175.6012. Lastly, I would like to reference the STAT2 book, The Building Models for a World of Data, and the University of Virginia Stat Lab linked here. Thank you all for watching. I hope this video was helpful and look forward to seeing you in subsequent videos.